So then we did all that for the momentum part of it. Great. This is a heat transfer class. Let's do part of this for the thermal equations. So you know, it's really similar. The process is really similar to what we just did, just going to be in terms of temperature now. And there are a few other kind of small complications that we have to deal with as we go through. Okay, so let's take our example again. You know, we're not solving for anything where there's something especially interesting happening. It's just a boundary layer growth over a flat plate. There's not mass flux into it. There's not shear driven flow. There's not conduction at the boundary. It's pretty straightforward. So we're going to go through again, assume a functional form for T. I'll substitute that in, do the evaluation for the different criteria that we have, solve the ODE in terms of the thermal boundary layer thickness, and then estimate heat transfer coefficient and Nusselt number based on that. All right, so here's our governing thermal equation. That's really hard to see, sorry, but if you just look again to remind ourselves, we have four things that we include in this integral solution. We have the enthalpy change due to fluid, the sort of the energy associated with fluid motion, the energy that's carried by the fluid as it's flowing. That's the enthalpy change term. Then we have energy due to fluid motion in the term there. Then we have a conduction term that's, say, conduction at the surface or conduction at the edge of the boundary layer. We're always going to have conduction at the surface, right? This is typically why we're looking at these for heat transfer. So that's almost always going to be something we care about. We often don't have conduction at the edge of the boundary layer. So like, what would it look like if we did have conduction across at the edge of the boundary layer? Maybe there's the boundary layer is fully developed and there continues to be a temperature gradient that's enforced or something like that. Maybe in a reacting flow, you might have something where you care about that. And then the last term, which is often neglected, is viscous dissipation. Viscous dissipation is, again, you'd want to justify that you can neglect this. And to do that, you look at the ratio of the Eckert number to the Reynolds number. Right, so look at that number. If that's small, you can neglect the term. So it's almost always small for a lot of the things we care about. Okay, so for our problem, we have to go through and say, what is our solution going to look like? Well, we can get rid of what? We're not allowing any energy coming in due to fluid motion in the y direction. We are not conducting at the outer surface, and then we're going to assume Eckert over Reynolds justifies that we throw away our viscous term. So then what are we left with? We're left with this term here and this term here. So that becomes, maybe I don't need to rewrite it, but that's the equation, right? So we have one thing on the left and one thing on the right. Okay, so then what are we going to assume? So let's assume for our temperature distribution, just to be consistent with the velocity assumption that we did, let's again assume it's a second order polynomial, go through the same analysis. You don't have to make that assumption. You can make it more complicated if you want to. For our purposes, let's just do it that way. So T minus TS over T infinity minus TS, that's going to be our normalized temperature distribution. And that's going to be some function of y over delta T. Right? So let's just write that function of position y over the boundary layer thickness, delta T, the thermal boundary layer thickness, not the momentum. Okay, maybe that's obvious, but it becomes important. So let's make our assumption that T minus TS over T infinity minus TS is equal to A plus B times y over delta T plus C times y over delta T squared. That's what we think this is going to look like. Now let's go through and enforce some conditions. All right, so first condition. So first condition, let's see, we know that at the edge of the surface, we're at the very interface between the surface and the fluid, the temperature of the fluid has to be equal to the temperature of the surface, right at that first molecule adjacent to the wall, that's true. So, so at the surface, we are going to say T at y equals 0 is equal to T S. Our second condition that we might want to say is at the edge of the boundary layer, we want the temperature to be equal to the free stream temperature. So we would say T at Y equals delta T is equal to T infinity. The third thing we might want is, let's see, again, like the shear stress, where at the edge of the boundary layer, we want that to be 0. At the edge of the boundary layer, we probably want heat flux to be 0. We probably don't want conduction occurring at the edge of the boundary layer, at least for the flow that we have. So that's going to be minus K dt dy. So our heat flux given by Fourier's law in the fluid, right? This is Fourier's law applied to the fluid at y equals delta T is equal to some specified heat flux Q dot double prime Y equals delta T, which is for our problem 0. Again, if you wanted conduction, you just make that not 0. Then that's as simple as that. These are, I think, in probably priority order, these are probably the things you'd want to enforce first. So if you had a second order polynomial, maybe you only want to do the, first order polynomial, you only do the first 2. By the way, if you have a 0th order polynomial, you can do one thing, and then your entire temperature distribution is flat and not interesting. So you don't do that. But okay, so first 3 and then 4, you can continue on after this. The fourth thing, if you want to do that, would be, let's see, the differential energy equation is satisfied at the surface. So differential energy equation satisfied at the surface. And so that would be something like this. Rho times C U dt dx plus V dt dy is equal to K d squared T dy squared plus mu du dy squared u dy squared, all that evaluated at y equals 0. So that's the equation we would want if we had enough coefficients to satisfy. So based on this, we would go through and enforce these. I'm not going to do it, but you end up with this equation here. Right? This is our solution if we go through and enforce at least the first 3. Right? In order to enforce the first 3, this is our temperatures. It looks really similar to what we had for the velocity solution, but again, in terms of normalized temperature. So you can go to the book, you could do the same thing without actually going through the analysis. If you know your conditions are in that order and lining up that way, this is what it ends up looking like. Again, third order polynomial, you're going to be doing a lot more algebra, but it's possible to do it. Things to point out here. So if we assume second order polynomial, you'll note that the heat flux equation is this. So this is saying that my resistance is actually kind of on average corresponding to delta T over 2. Right? When we've done our models before, we've set our thermal resistance through, like in the 1D transient conduction problem, we say the thermal resistance corresponds with delta T, right? The thermal penetration depth. This solution, and this actually our assumption of what the temperature profile looks like, leads to an equivalent heat transfer relationship that says my resistance is actually based on delta T over 2. So don't get too thrown off by that. It's something that falls out of our assumption of what the temperature profile looks like. Okay, so let's look at the quality of solution again for these different assumptions. Linear is going to be highest error. As you go higher and higher, you get lower and lower error. The magnitude of the error is really similar to what we saw before. So not too much else to say here. Let's just go through and actually enforce this then. All right. So here's our assumed temperature profile, if you can read it. What we're going to do is we want to get to a point where we can have our thermal boundary layer in terms of delta T, right? And what we care about is not just that we've got a temperature distribution. We want to be able to calculate things like heat flux and things like heat transfer coefficient. So to do that, how do we relate temperature to those things? Well, we're going to use Fourier's law to do that. So we'll start off by writing out Fourier's law for this problem. So Q dot double prime S is equal to minus K T dy at y equals 0. Again, this is Fourier's law in the fluid. Laminar flow, the mechanism for moving heat in the fluid, is conduction in the y direction. So it is Fourier's law is valid here. So we're doing Fourier's law, and then we substitute in our temperature solution, and we get minus K d dy of our, let's see, we bring T infinity minus TS over to the right, take the derivative of TS, that goes away. So then we end up with just T infinity minus TS times 2y over delta T minus y squared over delta T squared. All of that, let's see, yeah, this whole thing here evaluated at y equals 0. So this whole thing here. And that's equal to, on the right-hand side, what? K Ts minus T infinity times 2 over delta T. Okay, that just comes from our original equation, or our integral equation that we started with here. Okay, one thing to note is that we have, in here, we have T infinity minus Ts. For our given problem, if we look back, I think we were assuming that Ts is a constant. That was something we stated in the problem. The problem statement is, let's develop this for a situation where Ts is constant, not changing as a function of x. So it certainly isn't changing as a function of y, neither is T infinity, but it could change as a function of x, right? You could have a situation where maybe we want to specify Q dot double prime instead of Ts. So Q dot double prime is fixed. The kind of cool thing about this integral approach is it's really flexible. So I can come in and I could say, as long as I have a relationship to go back and forth between Q dot double prime S and T infinity minus Ts, I can use either one, right? I just have to keep in mind what's varying. So I could just use this relationship where we say Q dot double prime S is equal to K Ts minus T infinity 2 over delta T. This is going to be equivalent. We can use this either way. We could say Ts minus T infinity is equal to Q dot double prime S, so C times delta T divided by 2K. Right. And again, where did this come from? This came from our assumed temperature distribution and applying Fourier's law. So this has to match the assumed temperature distribution that you use. So we can go either way. So we'll start by saying, all right, Ts minus T infinity is, in terms of the things we know, Ts minus T infinity is constant. So we're not going to, substitute in Q dot double prime for that, but any place we see Q dot double prime, we can use this relationship. Okay, so let's move to the next step here. So we're going to take these things, our temperature distribution and our heat flux. Let's see. Oh, you know what? I think I skipped a step here. Just see. No, we're okay. So let's go back. So what we're going to do is let's take our differential equation. Yeah, this is the next step. So our differential equation from the integral solution was this: d dx integral from 0 to delta t u times t minus t infinity dy. That's all equal to Q dot double prime S over rho times C. Okay, that's from our integral solution. So now we have a temperature solution. Sorry, scroll down too far. We have our temperature solution here. We can substitute that in right here. We have a relationship for Q dot double prime S right here. So we can substitute that in here, just like we did the same thing for tau. Or we're trying to get to ODE that we can solve. But we're still left with actually one thing we don't know. One thing we don't know is U. So in order for us to solve the energy equation, the integral form of the energy equation, we have to make an assumption both about the energy form, the temperature distribution, but also the momentum form, the velocity distribution. So we happen to have already done the velocity part. So let's just go through and use our previous assumption for U, which was what? U over U infinity is equal to 2y over delta m minus y over delta m squared. All right, we're gonna do that. So let's go through here and make that substitution. What we end up with is a final solution here that looks like I actually wrote it out here. So rather than make you write it out again, it just is right there. So we're substituting in our temperature. You can see temperature here. Our temperature is here. Our heat flux is here. Our velocity distribution is here. All right.